Okay, so for today's discussion, what we're going to discuss is nomenclature, or how do we name different compounds. So let's start with the simplest example, and this will be for binary inorganic compounds. Okay, so a binary inorganic compound will be when it's formed from just two elements. So the way that these are named is we list the cation first, followed by the anion, but we drop the ending of the anionic element and we add "ide." So for instance, NaCl, that is sodium and chlorine, but we don't call it sodium chlorine, we call it sodium chloride. Aln, we don't call that aluminum nitrogen, we call it aluminum nitride. Let's look at the example that we explored last time, MgO. We're not going to call that magnesium oxygen. We would name that magnesium oxide. Okay, so let's go ahead and look at a slightly more difficult case. And this will be whenever you start to combine an element and a polyatomic ion or two polyatomic ions. Okay, so this is whenever you have more than two elements. Okay, so you're going to follow the exact same format, except this time whenever you start to name the anion, if it's a polyatomic ion, you don't drop the ending and add "ide." So for instance, if you look in table 2.5, so that's table 2.5 in your OpenStax book, or you can explore another table in the CK12 platform. What you'll see is they'll have a list of all your polyatomic ions. So for instance, PO4 3- is phosphate. So here, this particular compound, AlPO4, is aluminum phosphate. One of the things that you should note is that there are polyatomic cations, but the most common ones that we'll use would be for NH4+ and H3O+. NH4+ is called ammonium, and then H3O+ is called hydronium. Okay, so but otherwise, let's think about this. If we had, for instance, let's say we had CaCO3. We aren't going to call this compound calcium carbon oxygen. The cation is calcium. Okay, so then what's CO3? Well, this is more than two atoms. So we need to look in our table of polyatomic ions. What we'll see is this is called carbonate. So this compound would be called calcium carbonate. Then we will not focus on this, but I want you to be aware that for organic compounds, there's a whole bunch of different rules. You look at how long the carbon changes, if there's any functional groups, if there's a cycle formed, if it's a ring. This is something that you would learn in an organic chemistry class in college. So let's go ahead and look at nomenclature for metals that occur in the middle of the periodic table, so for transition metals. Okay, so let's go ahead and consider things where there are multiple oxidation numbers. So I want to look at these first two examples where we have FeCl3 and FeCl2. We can't call both of these compounds iron chloride because they both have different chemical formulas, okay? So how are we going to name these? Because they're going to behave slightly differently because they have different formulas. Well, what we should note is they both have iron and they both have that chloride ion. So if chloride has the same charge, so that must mean that the charge on iron must change, because if we look on the periodic table, we'd see that chlorine is a halogen and it's going to have an oxidation number of -1. It's going to have a charge of -1. So how do we account for this change? Okay, so what we're going to do is we're going to kind of work backwards from what we've been doing whenever we're looking at the binary inorganics, and we would try to do the swap, drop, and simplify. So we tend to work backwards here, and sometimes some former students will call this the swap, hop, and multiply. So what we're going to do is we need to work backwards, and we need to try to make sure that we get the correct charge on the anion. So if we move working backwards, so we're going to swap the subscripts and then raise it to the superscript and give it charges, we would have Fe3 plus and Cl minus. Okay, so for naming this, because we're able to go on to the naming stage because chlorine has a -1 charge, so that satisfies that requirement of it being the chloride ion, so we don't have to multiply by anything, and we'll look at some examples where we have to do that in a little bit. So how would we name this? Well, we need to specify what the charge is on iron, so this would be iron, and then we put the oxidation number in parentheses and in Roman numerals, so this would be iron 3 chloride. Or if you were looking it up in an older textbook, they might use ferric chloride. We won't differentiate between ferric and ferrous. Ferric means the iron has a 3+ charge. Ferrous means the iron has a 2+ charge. We will use this method where we put the oxidation number in parentheses. Let's go ahead and try the next one where we have FeCl2. So if we work backwards, okay, so we swap, hop the charges, so we have Fe2 plus, Cl minus. Okay, so this satisfies the criteria that chloride has a -1 charge. So we would have iron 2 chloride, or ferrous chloride. All right, so this is how we would distinguish between transition metal where there are 2 different oxidation numbers, or this will really work for anything with multiple oxidation numbers. All right, so what we want to do is, so anytime you're asked to find the name of a chemical compound, whenever we put the charge in parentheses, that oxidation number in parentheses, we call this the oxidation method. Let's look at one last example. So this one is we have copper, and then we have the phosphate ion right here. But again, the phosphate ion is a polyatomic, so whenever we start to work backwards and we look at the charges, we need to put the charge on the outside of all that. So right now we have Cu2 plus, and then PO4 3 minus. So if we consult our table for the polyatomic ions, we would see that that phosphate is supposed to have a 3 minus charge. So we would name this copper 2 phosphate. And note the way that this formula is written, that this 2 shows us that there are 2 phosphate ions. So since we're looking at trying to figure out what ratio these combine in, since copper has a 2+ charge and phosphate has a 3 minus charge, we will end up needing 3 coppers and then 2 phosphates. So let's go ahead and look at an example with manganese. So we have MnO2. Okay, so at first glance, if we were working backwards, we would have, see, don't confuse manganese and magnesium like I just did. As we're working backwards, we have Mn 2 plus O minus. So at first glance, we would say that we have manganese 2 oxide. Okay, but wait. This is incorrect because oxide has to have a 2- charge, and this only has a -1 charge. So what we need to do is we need to multiply everything by 2 so we can have a 2- charge. So we have O2- and then this 2+ would turn into a 4+. So we'd end up with Mn 4+ O2-. This satisfies the requirement that the anion has the correct charge. So we're ready to name this compound, and this would be manganese 4 oxide. So watch for that if you ever need to multiply through to get the correct charge on the anion. Okay, so we can also use this oxidation method for molecular compounds or covalent compounds. So for instance, N2O, this would be known as nitrogen 1 oxide, because if we start to work backwards, we would have N with a +1 charge, oxygen with a 2- charge. Okay, so for the next one, no. Nitrogen 2 oxide, if we were working backwards, we'd have N+ and O-. But just like that last example with manganese oxide, we'd recognize that we need to multiply this by 2. So it's going to be nitrogen 2. Okay, this next one, N2O3, if we're working backwards. So we swap pop, we have N3+, O2-. So that satisfies the requirement that the anion has the correct negative charge. So we would have nitrogen 3 oxide. Then this one, NO2, we work backwards. We end up with N2+ O-. Oh, but wait, the oxygen, that oxide doesn't have the right charge on it, so we need to multiply by 2. So we end up with nitrogen 4+. So we'd have nitrogen 4 oxide. And finally for N2O5, as we work backwards, we would have N5+ O2-. The oxide has the correct charge, so it would be nitrogen 5 oxide. Okay, so there's actually another way that we can name these covalent compounds, and it really depends on the compound as to which way you can name it, because sometimes it's more convenient to use the oxidation method, but sometimes it's more insightful to use a prefix. Okay, so let's think about carbon monoxide. Okay, so that has the formula CO. So we have 1 carbon and then 1 oxygen. So we use the prefix mono for 1. Now if we look at carbon dioxide, so that's carbon and then 2 oxygens. So one of the things that you should note is that whenever we're doing this, that if there's only 1 cation, we do not name carbon monoxide monocarbon monoxide. If there's only 1 cation, we just say what the element is. Okay? And then we put monoxide, so we specify how many anions there are. But if there's multiple cations, then we do include the prefix. And the common prefixes is for 1, it's mono, for 2, it's di, for 3, it's tri, for 4, it's tetra, just like the game Tetris. All of those blocks are formed off of 4 little blocks. 5 is going to be penta. 6 is going to be hexa. 7 is going to be hepta. 8 will be octa. 9 will be nona. And 10 will be deca. All right, so what I want to do now is, now that we have this list of prefixes, let's go back and name the nitrogen and oxygen containing species with the prefix method. Okay, so you guys will be responsible for being able to name these using both methods. But again, please remember that we do not include mono with the first cationic species, only the second anionic species. Okay, so nitrogen 1 oxide. We could also name that dinitrogen monoxide. Second compound, NO, we would just name nitrogen monoxide. The third compound, N2O3, we would name dinitrogen trioxide. The fourth compound, NO2, it would just be nitrogen. We don't call it mononitrogen. It should be nitrogen dioxide. And the final compound, N2O5, would be dinitrogen pentoxide. So you're going to have to use some judgment on these. It's not pentaoxide. So like pentoxide, hexoxide, we are going to leave the A off of some of those. All right, the last thing we want to discuss for today's lecture will be diatomics. So we've looked at monatomics and charges on single atoms. So a monatomic just means there's one atom. Okay, so now let's look at diatomics. So there are two different types of diatomics. There are heteronuclear diatomics and there are homonuclear diatomics. So heteronuclear diatomics means there are two different species. Whereas for homonuclear diatomics, it's the same species bonded to itself. There are 7 naturally occurring diatomics. And what we'll have to look at here is that there's an easy trick for remembering them. If we start at element 7 on our periodic table and make the number 7, so we go nitrogen, oxygen, fluorine. Okay, so nitrogen, oxygen, fluorine. And then we go all the way down. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, plus hydrogen. These are all of the elements that exist as diatomic. So N2, O2, F2, Cl2, Br2, I2, and H2. So these are your 7 homonuclear diatomics. They start at element number 7. Recall that nitrogen has an atomic number of 7. If you draw the number 7 on the periodic table, there are 7 of them. Only 5 of these exist at room temperature. That would be the hydrogen, nitrogen, oxygen, fluorine, and chlorine species in the gas phase. But just so you're aware that whenever we talk about in the future a reaction of oxygen, we say oxygen combusts something, we're actually talking about O2. If we're talking about O, we're going to have to mention something about it being atomic oxygen. So these are some things that you will need to commit to memory. All right, so next time what we'll do is we'll start to explore naming compounds that are acids and have a slightly different naming convention. But that's it for today.